Topic for this month. Um, having been making modifications to special relativity lately, I decided to go back a little bit further, like about 2,400 years, and get into the issue of some of the fundamental concepts of mathematics. Uh, the connection is actually quite strong, so it does sometimes merit a look at what you think are just extremely straightforward concepts. And the concept I want to address first, which is really kind of the first incarnation of the idea of an infinitesimal, of an extremely small, infinitely small, however you want to define it, object, was the Euclidean point. So one of the most famous, most translated, and most remarkable books in history, The Elements of Euclid. I am always impressed at how deeply the Greeks thought about that, not just the Greeks, mathematicians in India, people in China. There's so many places in the world where ancient thinking was extremely deep, very profound, and they thought these things through to levels that often we don't these days. So Euclid in the Western world was certainly one of those people. Massively translated book. I think a total of 23. The first six are often the most commonly distributed. But he looked at these issues, and there was more science involved with this than we tend to realize. The Greeks were scientists. They were not just thinkers only. That's a bit of an illusion that we have because so little of their work survives. It tended to be, captured by individuals instead of taught in schools when there's some special trait or ability they had. But unfortunately, we've lost a lot of the scientific aspect of what they did. But we do have records of books like The Elements of Euclid. And before you even get to the various parts that often are debated, like the definition of a parallel line, first you have to get through the definitions. And I think the definitions are under-recognized as another point, literally, where you have to consider from a modern perspective what's being said with these. So the first four definitions: a point is that which has no parts. A line is length without breadth. The extremities of a line are points, saying that a line goes between them. And a straight line, which is actually the first definition of concept of length, a metric. This is where you get into a metric, is that which lies evenly between its extremities. Oh, is there a lot to unpack in those simple definitions when you look at it from a modern viewpoint of relativity and quantum physics? Because many of these seemingly simple points that seem so intuitive actually have a lot of complexity behind them. The first point I always like to point out is just look at the words. What was Euclid saying? His definition of point: what is a part? And what does it mean to say that an entity has no part? He clearly had a visualization in his head of what he was talking about. And it's not too difficult to get an idea of what it was. He was saying that a point is something that's kind of ball-like, that's spherical. That's the part about has no part. He's saying that there's no structure. More precisely, he's saying there's no orientation to it. It doesn't have the ability to point in a particular direction. It's not an arrow. It's not a cube, which is a combination of arrows. It's something that is unusable if your idea is to try to point out a direction. The other thing he's saying is that you want to make it as small as possible. The smaller, the better. So if you were literally trying to devise a metric system of some sort, first thing you would do is you would, say, well, I can't have a unit on my ruler that's this wide. I need to have an extremely tiny measurement to show what that ruler is actually trying to say. So you shrink it. And this is a very understandable operation. You take it, you find a smaller and smaller example of a sphere. So this is what he was doing in his head. But think on this a little bit. Is that as simple of a definition as it sounds like, or is there something more going on here? And I would say absolutely there's more going on here. This is calculus. He didn't have the terminology for it, but he's talking about an infinite limit of reducing a shape to get to a point where I keep saying that, I don't mean that as a pun, but to get to a point, to get to something that captures this concept really of location in a metrical space. So there is so much going on in this single definition. And yet, to this day, we tend to think of it as just like, well, that's obvious. And that's the danger, is because many things that we find obvious in the physical world are actually very specific combinations of circumstances that don't necessarily apply in all situations. So the structure that he was doing is really something more like this. We have lots and lots of things called atoms, which the Greeks, being the Greeks, they thought about this and they came up with some very good arguments for and against whether atoms existed. So they were aware of this, not that they didn't know about this. And they also had substances like glasses or even just ordinary unstructured materials of a variety of sort. Amber would be an example that have no orientation in how they look. Now, if you look at a crystal, you got a problem because those have orientation. And clearly, Euclid was aware of that. He was saying, like, no, no, you can't do that. You can't have a cube. Can't call it a cube because as soon as you say a cube, you have different kinds of cubes, which is interesting. Euclid was thinking in terms of symmetries, what we would now call a symmetry. So you're saying you've got to have spherical symmetry, not these symmetries that just go in different directions. So his idea was based on something that planetary classical physics gives you in abundance, which is an object with a lot of atoms. The atoms are so small, there's just no hope at that time period of seeing them or of detecting them directly. You reduce that, you keep shrinking down till you get a tiny little dot of sand or dust, which is kind of, that's your location that you're trying to mark out. So this is the deeper intuition that comes behind what Euclid did came from the material world. They knew that materials were imperfect, so this was not a surprise. Euclid knew that a substance was not a perfect representation. Of course, we have the classic Platonic viewpoint, which says exactly that. It says, yeah, you got these grubby material things, but inside of that, there is a perfection that we can do. So the point is, they were saying that, yeah, you can't really do with a grain of sand. They knew that. That's straightforward for people who thought that deeply about things. But they could say that, yes, but it's an unending process. We can hypothesize that you can continue that process beyond the naked eye, beyond any limit that we can see. And for the Greeks who believed in atoms, from which we get the name, the undividable, which of course is divisible, but they can take that and say, yeah, but even then, you can keep going smaller. You can go to some infinitely precise location in a three-dimensional space, which is a space they were familiar with. So the whole idea is take away the grubby, icky, lumpy matter, which is what Plato did emphatically, and you have this beautiful structure, and everything is perfect, and you're good. Is that quite right? Well, there's a little problem there. One thing that Euclid and the Greeks could not have known about, did not know about, of the many things they did figure out, this was one that they did not, is that this thing called relativity. And here's an interesting little quirk on a definition that fundamental is violated when you apply relativity to it. Why is that? If you're familiar with Lorentz contraction is a relative thing, how the contracted object does not see itself as contracted. However, the contraction is entirely real in the world in which it's being viewed. If you put a train traveling at 0.866 light speed, I believe that's the right figure, going down a track, that train will be half the length on that track at any moment that it was before. This is not an illusion. It's not an illusion. So when people talk about relativistic contraction, please realize that even though from the different perspectives, you see different things. And that's a fascinating issue right there that's caused all sorts of paradoxes over time. But it's a real effect. And that real effect violates the definition that Euclid did of a point, because suddenly the point now has direction. And it's a simple point, and yet it's intriguing. Euclid could not have known about that. So the cases remain unique if something is moving. And your definition of point is already a little bit inadequate for that situation. Does it make any difference? So Euclid never met Einstein. Of course he didn't. But think of how deeply this man from over 2,000 years ago thought about everything. If he had known what Einstein knew, if he was aware, if he saw on a daily basis that he could see, if relativity, if the speed of light was 60 miles an hour and he could see things constantly being compressed as he walked down the street, I guarantee you Euclid would not have come up with the same definition of a point. He would have had to accommodate that because he would have realized that something's not right here. Because when a chariot goes down the road at some high speed, if the speed of light is 60 miles an hour, 60 kilometers, I'll say 60 kilometers an hour, then it's not going to give you the same view of the world that he had. So Euclid would have realized something was wrong with his definition. So what does that leave us with? It leaves you in an interesting bit of a conundrum. Euclid had very good definitions for classical physics. What's classical physics? Classical physics has this perfect framework of X, Y, Z that's invariant in all directions. Newtonian physics is a later incarnation of it. So the definition of a point, and this I find remarkable, as soon as you define a point, you have actually locked yourself into a single observer perspective. You can have objects moving in it, but the points by which you're doing metrics all belong to a single observer. So think of this in terms of if your mathematical system is based on a foundation in which it is assumed that a rigid Newtonian space framework is what reality is, how is that going to affect your math? And the point is, you can't separate those issues. The intuitions that went into the very concept of space were in fact derived from this kind of thinking. It gets a little bit worse because another thing that Euclid could not possibly have known about was the fact that there is something called quantum mechanics. Now, relativity is just a distortion. So absolutely Euclid could have handled that. If the speed of light had been lower and he had been watching people, relativistically contract as they ran down the road, Eureka, the fellow shouting Eureka would have been physically shorter than he was before. He would have accommodated that, and he probably would have had the mathematical tools to do that. Now, that would have been remarkable because then you would have had relativity literally millennia before that. There was no lack of smarts to do it. Euclid, I have little doubt Euclid and some of the other folks could have done it if they'd known and seen on a daily basis the effects of Lorentz contraction. But since they didn't, they missed out on that. Quantum mechanics is worse. Quantum mechanics is not something anyone could have anticipated. It just doesn't show up. There are a few very small hints from wave mechanics, from a few areas where you could kind of get an inkling, but this one just came out of the blue. And what did it do? It annihilated the concept of a free point in the physical world. Now, again, there's two different worlds here. You talk about the mathematical abstraction world, but you also have to recognize that that world has been inspired by very, very real physics, the physics of classical mechanics in which Euclid was buried. So the points that he talked about really fall apart at about the level of what we call atoms. And a little classic figure from Feynman lectures is the repulsion that you get, which is actually a Pauli exclusion. It's not electromagnetic. If people tell you it's electromagnetic, that's wrong. It's a Pauli exclusion effect that goes on, that all this simple, easy, not difficult movement that you can have between atoms. Two atoms can approach each other from enormous distances and come very close together. But when they get to that point, there, this happens. You see this sudden jump in which the repulsion just goes to infinity, almost not literally, but it goes extremely high. And the concept of the point as defined by Euclid in material world no longer works. Now, we know that there's particles inside and we can repeat this process all over again, but you can't get out of it. You can't escape it. At some point, whatever you're defining as the point, if you want to call it an electron, if you want to call it a photon, if you want to call it a proton, protons actually have size though. If you want to call it any of these items, you still have this quantum limit that when you compress things, strange things happen, the biggest of which is that repulsion and energy costs go to infinity. So Euclid could not have been aware of that. Whereas in the case of relativity, he would have had a difficult time dealing with this with the mathematics of that time also, because it gets heavily into wave duality. So, which is worth pointing out. In all examples of metrics from the physical universe, and again, the only fully working system we have is the physical universe. That should not be taken lightly. Because if the physical universe inspired concepts of space, metric, points, lines, then we have to acknowledge that it also should inspire other things that are related to those. And one that gets missed very easily in many forms of analysis, not all, but many forms, in fact, Fourier analysis, there's forms of analysis dedicated to this, but many of the traditional real continuum mathematics fail to acknowledge this very well, which is that locations always have this weird duality. What looks like a point in one definition of metrics always also looks at something very spread out in another set of metrics. This is the wave-particle duality. A better way to say it is it's a dual space duality. So we have things called Bose condensates, which look like shiny balls floating in space. In our space, they look like shiny balls. In a wave space, they have a very different appearance. They actually look like they're localized in a different fashion in this idea of momentum space. So this duality pops up everywhere. More recent incarnations have talked about it on, I think, in ways that are in many ways distortions of this fundamental. This has always been there since the early days of quantum mechanics. Every quantum mechanic wave function has a dual wave function. So if you have a wave function for a particle in space, you have a wave function for the same particle in momentum space, except it's not a particle there anymore. It's something different. It's a shell-like shape. But you have these dualities that are inherent in the definitions. Why is this important? It's telling us something about the nature of metrical spaces. It's saying if you want to have a metrical space, you need to understand waves. Why? Because waves, just like on a radio dial, you have different wave frequencies, you get different locations in your dial. Really, that is a Fourier transform. The same thing is going on with the metrics in the real world. So the question you want to ask is, does my analytical framework sufficiently encompass this idea that I recognize duality of location as a fundamental? And of course, the answer is, for most forms of analysis, the answer is no, because location, 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 we tend to think that way because that's the world we see. Now, into the actual history, Euclid, I would argue, is the first infinitesimal that's well defined, simply because he talked about a point, which is an object that is an infinitesimal. Now, Zeno, he liked to challenge people, and you have the classic. He has several examples with arrows. You have the turtle one. You have I think it's Achilles. But his point was that if you keep dividing things smaller and smaller, you get this interesting conundrum in which no one ever, the faster runner never quite passes the tortoise. Now, by doing this, the quantities he was talking about, both in time and space, were these ideas infinitesimals, extremely small quantities. So he brought that up, and of course, to this day, we still call it a paradox. It still causes, it's funny, after all this time, it still causes problems because we still have this idea of like, well, does that mean that space is quantum? Do we suddenly jump past the turtle? Is it a bunch of quantum leaps? Is there some version of this that we're missing? Is there some level at which this ceases to be an issue? Those are still, to this day, questions that get debated. So interesting how some of these deep thinking people from that far back still have left things that we look at. Let's jump a couple millennia into the future, and a fellow named Leibniz, co-founder with Newton of the calculus. And I like his version, and I think most people who have taken, for instance, engineering courses, who have taken practical courses in calculus, also like Leibniz, because he came up with this kind of straightforward representation of an infinitesimal as, just as Euclid did, as a conventional object that gets shrunk down to a very small size. So the triangle and the slope is the one I always like because and of course, there are different kinds. You have rectangles. There's all sorts of different versions of this, but I like the slope. I love the slope representation because what it's saying is, yeah, you got a curved line. It goes up like this, but if you get small enough, you'll find out that that curve no longer becomes relevant. The change no longer becomes relevant. The second derivative becomes irrelevant, and the first derivative is the only one that you care about. And that's a marvelous property because it says, well, I can't get a perfect answer, but if I keep shrinking these little triangles down smaller and smaller and smaller, there's a smoothness effect in which I get rid of the higher order derivatives. And I just wind up with a nice, straightforward concept I can understand, which is an extremely small triangle. And then you stitch all these triangles together and you wind up getting all sorts of beautiful properties, mathematical properties, which you can start doing conversions between your equations. You can come to conclusions that you would never have recognized had you not applied this calculus method. So Leibniz, it's an idea. His idea has never gone away. When I took calculus courses, I was taught with this style of thinking. But at the same time, in the 1800s, an interesting thing happened that for a lot of people, not everybody, and for some people's textbooks, not the ones I use, all of that calculus got dumped, and they said, no, we're not gonna do that Leibniz stuff anymore. We're going to go back to a method that is not new. In fact, it's even older. It's 3,000 years old, which is you just use a limit of these lines. You add an additional point. You get closer and closer to that point. The points come out, and eventually the limit of that process gives you this tangent line. Now, if you are a pragmatic sort, if you're especially you have an engineering background, there's a very good chance you'll look at it and say, like, why are you doing that? You've added a new point that wasn't there. You've added details, mathematical concepts, the secants that weren't there before. And you can ask a reasonable question is, why are you doing this? This seems like an excessive complication. Well, there was a reason for that. And it has to do with the idea of what that line is, the same line that Euclid defined. So what happened, and I'll pick on Richard Dedekind. There's a number of people, Cauchy more famous, but Richard Dedekind in particular had a really interesting concept. He said that if you could use an irrational number and stick it into the middle of the number line, that would cause the number line to split into two well-defined pieces in which you can absolutely say every number on the left side is smaller, every number on the right side is larger. And by repeating this process, he was able to come out with a way to fill the number line in completely. This had been an issue before because the Greeks, they only used rational numbers. They used ratios. They didn't like this idea of these irrational numbers. They only executed one student for believing it. So the famous story about Pythagoras, I'm not sure if it's true or not, but it's an amazing story that when his student found irrational numbers, he was so upset they dumped him off a boat or something. So there's different versions of it. May or may not be true, but the point was they didn't like that idea. The Greeks liked the idea of rational numbers. And a number line with rational numbers is full of holes. It definitely is not complete. So Cauchy, Dedekind, others, they came up with this way of filling those holes. So instead of saying that, well, it must be little tiny pieces here, the little infinitesimals are actually real things with real length, in some sense, you could fill it up completely and all that disappears. That drove them to going back to things like, well, the lines are the only thing that counts. The perfectly differentiable lines, infinitely differentiable lines are the only thing that counts. That has had a lasting influence on a lot of what we do these days. The idea that lines are infinitely differentiable could not really come into existence until you filled in that number line and said the number line is perfect. So the line that Euclid defined is a perfectly filled line, despite the fact that the atoms run out. You know, you're going to run out of atoms. Here's a little side note on the Dedekind cut. And again, I'm naggingly, persistently going to bring in the idea that If physics has inspired the majority of the concepts, such as spaces, limits, points, that we use without question in mathematics, then we ought to look at what physics says about certain statements that we make. And one of the statements is very interesting. How many digits does it take to define a Dedekind cut in the real world? And the answer is infinite. How much time does it take to define a Dedekind cut? Infinite. Why? Because you have an infinite number of digits. You have an infinite number of information. You have an infinite number of bits, each of which takes some mass and energy. You cannot have bits for free. Anybody tells you that if bits are free, they don't require material, some kind of matter or energy, they're just guessing. That's anyone who's worked with real bits, you know that's not true. Information requires mass and energy. Empty space does not preserve or conserve any kind of information. However, you might say the structure of the space is, it doesn't conserve things. So think about that. If one Dedekind cut requires more mass and energy, which it would, than exists in the entire universe, which it would, because infinite digits, believe it or not, infinite digits means everything in the universe gets used up, and you're still not there. That's what infinity is. So you wind up saying that, yeah, so this makes the number line solid and completely continuous, but at what cost? The physical inspiration for this is actually rather terrifying because it says a single irrational number takes all that. We see this in pi because even we're not going to get to that. We're not going to use up the whole universe to calculate pi, but look at the computational power that people have dedicated to finding a larger version of pi. Now, the assertion is that pi just exists, and you can say as a limit it exists, but the idea that you say if you want to put it into a number line, you want to actually put it into a number line so that that number line is smooth, then all of these points like this wind up costing this incredible amount of energy and time to calculate. So the fact that you have a limit does not mean that the limit is calculable. And it's an important thing to look at in the inspiration. This one bounced back in the other direction fairly quickly because people go like, no, I like my infinitesimals. I like my little triangles. And a fellow named Abraham Robinson came up with this idea of hyperreals, which is kind of a nifty idea. It's not complicated. He's just saying that if you flip it around this way and you look at the equation here, you have absolute value of x is less than 1 over n. You can define a limit in which you get these numbers that behave nicely. They're infinitesimals, and yet they still behave like real numbers. So it's still a limit. It's a different kind of limit, but it's an interesting way to kind of get back to that and fight back against the idea that no, we should just try this. These arguments, by the way, apparently get really intense. People throw more than shade. They throw insults at each other. They really get upset about some of these different issues. And again, the applied community, like the engineering community, they don't care. They just want a method that they can understand and they work. But the debates get quite intense. So lines. Lines measure distance. Lines are the whole concept of metrical space. You have points, but what you really want to get at is the idea of what is the lines. Now this is the part where I'm going to get a little interesting where I go with some of this, or a little unusual. Inspiration of Euclid's lines, surprise, surprise, is the same thing. You can have, say, a piece of fiber, a string. It has fibers. So you strip off the fibers, you get a smaller and smaller fiber, and eventually get this extremely thin fiber. And that's what you define as being your approximation of a line. Now, the trouble is that you have to do infinite reduction of that. So again, you have to squeeze it down to a very small, potentially infinite limit. And that's a problem if you're using atoms, because sooner or later, the atoms are going to break. You don't have enough atoms. I am going to make one little side note, because I've seen this argument, and I always find it very surprising that people will occasionally claim that the concept of superstrings, which are the 20 orders of magnitude version of quark orbitals using the strong force, is their actual origin. But superstrings sidestep the idea of an infinitely small point because it's a string. No, because the string still has infinitesimal width. That doesn't solve anything. It just that is an incredibly bad argument. So you can argue for superstrings however you want, but don't argue that they're okay because they're not infinitely small. Yet, well, they still are. You either have to define a width of the superstring or you're going to violate the same issue I've been talking about, which is reality in every case we've seen gets very stubborn when you try to shrink things to infinite width. And that includes strings. So here's where I'm going to say something. In fact, this is actually a little bit different from things I've said in some earlier presentations. But also, I think it's well worth pointing out. Even though Euclid's straight lines eventually wind up as this, the physical example that it comes out is you have two atoms and you have them separated, and somehow that defines a separation, which we can call a line or a metric line, a distance. And what I want to point out that's a little different from some things I've said before is that what goes on between those two atoms is not a perfect vacuum. Now, I've said before, it's so close to a perfect vacuum that you don't need to worry about it, but that's not quite true. There is the same fade-off curve that I mentioned earlier, the K over R7. That's a steep fade-off. Wow, that really gets weak in a hurry. It's still there, and it's an interesting effect that says there, yeah, there's a little bit more going on there than just saying you got two atoms at a free distance with that. Now, the atoms also do not give a very clear definition of a line. You have quantum uncertainty. The location of the atoms quickly grow indeterminate. You have the dispersion effect for the momentum states of those atoms. It just means that if you have an atom sitting in space with nothing else going on, you set it there, you set it there perfectly, it doesn't matter. Dispersion relationships between the internal states, the states, the momentum states, means eventually that the location of that atom will grow and expand, and you will find that you don't know where the atom is anymore. So that affects this definition of line. If you try to make the points too small, you can't tie down the ends anymore. So general relativity says even more interesting things. If they're over a very large space, you can't even say it's a, quote, straight line. You have to go some more complex set of mathematics to describe the curvature for that space. So Euclid's line concept of straight line quickly becomes a lot more complicated, but also in an interesting way when you bring it to modern physics. Again, Feynman's lovely little diagram. You have this relationship where you have this perfect point illusion up to a point. So you don't have anything that works as well. Have to get that. You have to break it into smaller points, but you get this illusion of a point. But you still have these molecular fade-offs. This little long trail that goes off in the right, and that's the same one I showed in that previous diagram. Now here's it's interesting because I was looking at the famous essay, well worth reading, nice essay that Wigner wrote about why is mathematics so good at predicting physics? Great question, and he goes into some detail about that. But I was captured by a statement that he quoted from a student, a fellow named F. Werner, and I'm not, maybe Felix Werner. There's some ambiguity in most of the records I saw about who exactly this student was he was talking about. I'm sure someone knows. But this student, F. Werner, asked him an interesting question. And I liked the question so much I thought it was worth pointing out in this context. If physicists, and again, this is heavily edited, but I tried to be very careful to preserve exactly what he said. I just said it in easier words. If physicists abandon the phenomena they considered important in the past, which we all select, and instead focus on ones they view as unimportant, that we said, yeah, that doesn't matter, could you wind up with new theories that explain just as many phenomena? And Wigner was kind of floored by that. He said, well, it's a good point because he knew that we have a bias in terms of how to select these. So what I'm going to suggest here, and this is a hypothesis just to think about, is that instead of viewing the distance between those two atoms as completely empty space, maybe we ought to focus a little more on that tiny little remnant effect, the trail end of that curve that Feynman drew. and say, well, just because it fades unbelievably fast, does that truly mean that it's not relevant to how the universe works? And if you've seen anything about quantum, the idea of, if you want to call it wave collapse, I don't want to get into the whole terminology of you, but certainly we have something where things that once seemed to be big suddenly seem to be very small. And it's not hard to come up with cases of that. And that's based on incredibly small amounts of energy make that difference. That argues that maybe the part of the universe that we have considered unimportant might be a little more important than we think it is. And I'm suggesting that some of these bonding relationships, which are based on photons, these are actually covered by QED, but just at extremely low levels, extremely low intensities. Photons, by the way, are gauge bosons. That means they're three-dimensional, and that turns out to be kind of relevant to this hypothesis. So QED and the vacuum density problem. If you have this idea that the bonding force becomes vanishing small in energy, then you also have this idea that a lot of what QED describes is relevant only in cases where you have extremely high energy levels. So this is an idea that some of the QED math has fallen into a bit of a trap, and the trap is very easy to find. It's the Euclidean infinite line density trap, which says that all of spacetime is infinitely precise, infinitely detailed, even though we have no physical examples of that ever happening in the real universe. All events in the real universe require infinite time to do that, even for one point. They require infinite energy, even for one point. So, and this is something Feynman worried about. There's a famous talk he gave at Princeton, which he said that, yeah, all this detail doesn't seem right. It's probably something simpler like checkers. And he looked his whole life to see if he could figure out what the checkers were. But think of it, he won a Nobel Prize for QED, and he got a laugh in an audience of mathematicians, essentially dissing his own theory, saying like, yeah, this doesn't seem right. So the renormalization technique that he got a Nobel Prize for, if you have this idea of saying maybe these weak bondings are what really count, it kind of flips that upside down and says that, yeah, the QED doesn't really apply because there's no energy there to fund it, to make it going. That's a very different way from looking at it if you assume infinitely continuous space-time, which is where the whole QED model comes from. Now, I mentioned that bonding is interpreted. If you see papers about looking for the Casimir effect, the famous Casimir plates, I think everybody who's watching this has seen that. You have two plates, you have this force that pushes them together. The bonding effect that goes there is only detectable at surprisingly large distances. And the reason is you've got some interfering effects in between. So if you get too close, you're not going to see it. It gets wiped out by the signal by the van der Waals forces, and you just don't see it. So you actually have to get it fairly far apart, and then you can start seeing this idea of a Casimir force, which is a fascinating wave-based force, one of the most famous experiments in science, and also quoted very, very heavily as an argument for infinitely energetic space, the very thing that Feynman was a little bit reluctant about. Here's the quote, and I quote this on at least every other presentation because I think it's important. Casimir did not believe that space had infinite energy. He spent he must have had an interesting dance because he seems to have been reluctant even to call the Casimir force, and I think part of that was a feeling of reluctance that he didn't really buy it. So in one of the last presentations he made, in the last line of the last presentation, it's almost like a confession. It's like the guy on his deathbed. I'm gonna confess now. First, he says electromagnetic zero-point energy has absolutely been established. Yes, yes. Steve, I can't remember his Lamo. There's been some very good experimentation that has shown the existence of this force, and it matches the profile. But then he goes on and says this remarkable statement. Says there's a more modest view, which is The Casimir force is nothing but the most elegant final trace of ordinary molecular bonding cohesion. Oops, what? This is complete heresy. This is the opposite of what Bohr and everybody else was saying. This is saying like, no, there's no infinite energy there. In fact, it's nothing more than the K over R7 fall off line, and that's it. That's all it is. So it's incredibly weak force, almost entirely electromagnetic. It is entirely electromagnetic, but it doesn't go away. It's real, and it's part of the equation when you do it. I always love this one too because I had a whole bunch of diagrams. I'll show you a couple of them in which I was analyzing the Casimir force by splitting a piece of metal apart and then seeing what would happen with that. I had no idea that Casimir had the same thought experiment. So I loved it when I go this like, oh, right, yes, yes. That immediately resonated. So he says you break the chemical bonds, you break the van der Waals. Those are the confusing ones. The van der Waals are the classical type. And then you get a little far, there's this curious little tail, and that's where you see the Casimir force. So what does that look like? What was Casimir saying? What was this heresy he was proposing? Well, first let's get rid of the close range one. Van der Waals forces, you can see all sorts of complicated explanations of van der Waals forces. They're not complicated. If you have a bunch of magnets in a pile and you get the pile of little magnets close to each other, they'll stick. You know why? Because it's a magnetic equivalent to the van der Waals force. They're just rearranging themselves a little bit and say, oh, I see a north pole there, and they kind of shift around and go, okay, I feel better about that. So you get a little, not a real strong one, but you get a loss of energy. So you can mimic the van der Waals force using just little balls of these little round magnets, put two balls together and get them close. You can feel a slight attraction. That's van der Waals, magnetically implemented, magnetically mimicked. And that's what happens here. You have irregular charges at the atomic level. So you get within atomic scale, guess what? They start shuffling around, bumping into each other. So I'm going to move just a little bit this way. You move a little that way. That feels better. And so in a nutshell, that's what van der Waals is. So when I get rid of that one, that was the one that was first derived. And there's a second level that you see this, especially with metals. Metal plates were what Casimir focused on from the start. You have seen many a model that shows electrons as little particles going back in the metal. That's nonsense. That is not what happens. If that was what happened, you wouldn't have mirrors, you wouldn't have steel, you wouldn't have ductile strength, you wouldn't have reflection, you wouldn't have even the conduction, which seems like particles moving, is dependent on this ability of electrons to delocalize, to go into momentum space. When you talk about band electrons, the band that they're in is momentum space. And momentum space projected onto our space looks like waves, looks like skip roads, a little like one loop, two loops, three loops. That's all it looks like. And these are the base states of the electron. So all of these resonance effects get filled up by electrons. And this just happens. This is the marvel of metallic bonding, is that it's able to delocalize these and result in all sorts of interesting properties that you can't get with direct interatomic bonding. Ductility, I like the ductile aspects of what I like, because the fact that it's bendable is partly because the electrons don't know where they are. They're kind of like, they give you some flexibility that you don't normally get. So what does this do? Here's an effect, and I've seen some figures on it. I don't remember one. I saw one at, I think on YouTube that showed a very similar diagram. I don't remember what the context, but these things distribute charge, and it's a real distribution of charge. This is not just some imaginary, it's just like in atomic orbitals, those charge distributions, the cloud of charge, they call it sometimes. It's a very real effect. It has real repulsion and attraction effects. Well, this happens in a block of metal. And it's not obvious because you've got a lot of other stuff going on there. But your lowest energy electrons, the ones at the bottom of the band, they form these resonance points, and they actually wind up distributing the charge, so that you get these interesting wave-related charge distributions in the point. Well, why is that relevant to what Casimir said? Because it means that even when you get past the van der Waals, the more mundane van der Waals shuffling around type of attraction, you still have this long range distribution of charge that's not even. You average all these different charges together, and the lowest frequencies contribute the most. The highest frequencies just blur out to where you don't see them. But the low energy ones do wind up doing this. So you get this charge distribution that shows up between two metal plates. So why is that interesting? Because it means this attraction has a frequency dependence. It has components of the lowest levels of frequency of these electron frequencies are the ones that attract the most. Why is that important? What's the Casimir effect usually presented as? The Casimir effect is usually presented as an enormous amount of waves pushing in from the outside, and then the interior excluding the lower frequency waves. Now, by the way, there are so many problems with this simple diagram. People quote this and just as if it's no big deal. The pressure of those waves coming in should be infinite. And this is what gets missed. If this was truly, if space was filled with this level of intensity, you would have these things crushing these plates with an infinite energy. Casimir, in one of his actually, I just burst out laughing when I read it. He said, like, well, this is not a problem because metal plates just pass X-rays. What? This is one of his early papers. What? What are you talking about? That's not what happens. You can't just say the X-rays are there and they just go through it, so we don't have to worry. No. The gamma rays, if the gamma rays were there, they would have all sorts of effect. The X-rays would have all sorts of effect. So Casimir never really came up with a reason for the upper level cutoff of these things. So, and this is one of the reasons why I think he kind of carried this around and thought about it a lot for decades and said, like, yeah, okay, I know Bohr likes this, and Bohr is way more famous than I am or was. And I should kind of keep my mouth shut a little bit on this. And I think, and of course, obviously I'm guessing, but I think Casimir at some point kind of realized that what was really going on was, yes, there was a low frequency effect that caused attraction, but it was not the absence, it was the presence of a low frequency addition. Because if you take these two figures and compare them, you wind up with a similar sort of effect. You either get very low frequency, you get these large scale charge distributions, literally human scale, and they attract each other a little bit, just like they did in the van der Waals. It's kind of a giant version of the van der Waals. So these little charge distributions, which I call them polarons, and I don't know if they technically fully if they fully qualify as polarons, but it's a useful way of describing them because they certainly are similar to polaron quasi-particles. So you have these lumpy charges that occur mostly at low frequencies attracting. The Casimir plates show you have infinite frequencies with those same frequencies missing, and then that's the absence that causes those to do that. Now, I would ask you, just looking at these figures, which do you think actually works out as more probable? And I would definitely say the right-hand side. And I think that's what bothered Casimir, because that's essentially what he said. He said, yeah, you can't deny the fact that there's a low frequency exclusion, but I think secretly, I think it's just an attraction, residual Casimir force. So there's an explanation of Casimir effect that there's a good chance you haven't seen before. I don't recall if I published this one or not. I may have at some point. So I'm going to switch a little bit from that and suggest a different way of thinking some of this. There is a little YouTube video where someone had asked the question, I can't remember the channel's name, asked him the question, it says, what would happen if the Earth was made out of protons and the electron and the moon was made out of electrons? What kind of force would that apply? And is XKCD, I can't remember, the XKCD guy, I think, is the one who does that channel. And he said, this is the most destructive question anyone has ever asked me, because it would literally kind of blow up this part of the universe. It would just, the amount of energy that is involved in that is just so unbelievable that you can't qualify it. It would collapse into a black hole, first of all, because of all that energy. People underestimate how powerful the electric force is. It is, and Feynman did the same thing. He did a calculation of like 1% difference, and he couldn't believe the level of difference of how much it was. It was like two planets attracting each other when you had just a tiny difference in the number of electrons and protons in two objects. So the electric force is just staggeringly powerful. And we have this little trick in our universe in which things called protons and things called electrons both create forces, units of electric charge. Now, it's fascinating. They both come with the same unit of electric charge, but they do it in totally different ways because the proton has three quarks. The electron is just a single particle. It's very much like a quark. And the combination of the two gives you this almost matching of the electric force. But then they get close to each other, and unlike a positron and electron, they can't cancel. The force almost cancels, but they can't quite cancel. That almost canceling, if you look at that, and then again, going back to this Werner principle, look at the idea of almost cancellation as a powerful force, a powerful component of what makes our universe interesting and complex. Because when you almost cancel, then you wind up, you still have relationships between the particles. You still have relationships between the atoms. You still have some kind of photonic gauge boson relationships, even between particles that are very distant. But with the almost cancellation makes it unbelievably nonlinear. So that the vast majority of the force is in this tiny little atom, and then you have the itty bitty little remnant that peels off that way. And this provides you a way of defining distance in terms of relationships between particles in which certain combinations, an atom here and an atom there, can have an incredibly low energy relationship that allows them to move around freely, which is kind of our definition of space. So what I'm suggesting is this K over R7 free space is an important component of the behaviors that we think of as space behaviors, that we think of space relationships. I don't think it's a coincidence that gauge bosons are named that because they behave like three-dimensional relationships. Spin 1 gives you a three-dimensional relationship, and that is interesting because you can extrapolate that and see relationships with what we do in how particles relate in our universe. And this gets you out of the idea that you have to have infinitely costly, infinitely detailed lines, which is what Dedekind and others came up with earlier. Quick review, this is just an old slide, but a concept I will bring up again and again is the idea of a sparse information physics, the idea that the amount of information in the universe is finite, very, very finite. By information, I mean stored information. I mean information that persists. I'm not talking about momentary, transitory chaos, things that fade back to oblivion as soon as they happen. I'm talking about, the existence of an atom. That's persistent information. The existence of a proton. That's persistent information. The existence of relationships between those is persistent information. So the point is, all evidence we have in terms of actual physical design is that the information in those things requires a certain amount of mass and a certain amount of energy. So you can't just arbitrarily say, well, I'm going to do what I want to with that. And that has been done. I mean, the idea of saying that the surface of a black hole automatically becomes a bunch of bits. Yeah, you can make that argument, but it's a very spacious argument. It doesn't match anything we know about how real information works. Real information, needs mass, and needs energy. Needs fermions, by the way. So the vacuum becomes totally empty. This is where I would modify my own slide. I no longer believe this. This is a slide from a few months ago, but I intentionally left it in there that way. I said it was totally empty, and now I'm thinking like, no, I think actually QED still describes space-time. I think QED still applies between galaxies. But the way it applies, I think, is at an energy level so unbelievably low that we don't recognize them as that. that we actually have these relationships, and that the field where we see QED come in full force, where suddenly it just snaps into reality, is when you're in the middle of a particle collider, or you're in the middle of condensed matter physics. Often we'll have these versions where it's well funded by all the energy and material around. So you got a lot of information. So all of a sudden, all the waves, the hypothetical waves, become very real. They become very solid and well defined. So taking this kind of approach, you don't have these issues of field theory cutoffs. Uh, Field theory cutoffs, no matter how you look at it, if you define an arbitrary field theory cutoff, you're going back to the ultraviolet catastrophe. You're going back before quantum mechanics, because that's what everything was before quantum mechanics, was you had these, for some reason, there's an arbitrary cutoff that prevents things from going crazy. You'd be surprised how often the idea of these cutoffs shows up in modern field theories. And this is something that we need to look out for. So gravity and motion become relationships between these different objects. So analyzing continuum analysis. There's all sorts of analysis. How many different kinds of analysis are there? This is just a sampling. There's all sorts of p-adic analysis, by the way. I looked into that one once, and it's a fascinating little twist. I love the way it flips things upside down. There's, let's see, functional analysis, and some of the biggies, the calculus, of course, tensor analysis, calculus of variations, that's an interesting one. Non-standard analysis is where the guys went back to those hyperreal numbers. So smooth infinitesimal analysis, I need to look at that one a little. That's kind of interesting. In all of these, here's the point. In all of these, which ones of them specifically address the issue of whether the level of detail that is assumed in the mathematical construct is actually fundable by the system that you're trying to, that actually says, yeah, this can actually work. It can actually have this level of detail. And the only one I saw that really did that is computable analysis. And even then it's from a kind of quirky angle. Stochastic calculus, yeah, kind of, because it's saying about the relationships of sparse sampling. But the point is that most of these analysis methods are firmly, solidly based on the idea that real number lines are absolutely real in mathematics, which is not quite true if you try to instantiate the line. If you simply express the line, it's different from instantiating it. If you actually express the line, they all take infinite time. Pi takes, look at pi. How long does it take to calculate pi? We'll never finish calculating pi. True for every single number on the fully occupied number line. Number lines are expensive. They have a lot of cost. So the idea of a computable analysis of that, of a more introspective form of analysis that looks at information, says, how much information do I have? How much ability do I have to elaborate detail? What happens if I assume that I can't just elaborate infinitely on detail as if it was free? Because you can't do that in the real world. So why is it possible in math? The answer is really, it's just saying I don't care. I can define it, so that's all I need. But especially when you're trying to do versions of analysis that are applying to the physical world, we need to be a little careful. So the idea, information density analysis, which is IDA, which is also an organization in this area, is what I would suggest, is treat equations as generative programs. Why? Because they are. There's not that much difference between a bit of code and a bit of an equation. They both are statements of how you get to a result. They never actually give that final result. So you have an equation for calculating pi. It is a program. It says, here's how I can do it. Give me enough resources and I can do it. And see, this is where I think it gets interesting, because that is something that most forms of analysis are remarkably oblivious to. It says, what's the limit on that? The really good equations converge, give the same result over a huge range of scales. They have this invariance over scale. I think that is a sign of a beautiful equation. I use that word with caution because it's been misused so much, but a really good predictive equation converges over a huge range of scales. The equations that deal with space and time, relativity, general relativity, they have this convergent relationship that goes over this huge range of scales. That's a sign that you're getting a good little equation type programming going on here. And I realize it's heresy to say that equations are programs, but realistically, they always have an elaboration. And when you do conversions between you, you're really doing conversions and proofs of what's doable and what's not doable and what connects with these programs. If you have general relativity, you have extremely high masses usually. So you have very good approximations of continuum space, but also solid state condensed matter physics has very good fuel for these things. So a lot of times you see some most interesting quantum effects, not in free space, but in solid condensed matter. A very explicit example, I've given this before, but idea analysis, information density analysis of the block sphere representation of a qubit is awful. It's just dreadful because they just map the entirety of infinity to the top and they have one point at the bottom. And if you even a cursory analysis, if you're aware that information has a cost, you look at it and say like, that don't sound right. It's not a good way to represent a qubit. And yeah, it has nice mathematical properties, but being aware of the costs is a good idea. In contrast, a very Feynman-inspired technique I call two shadow qubits. This gives you a lot of the same, gives you the same intuitions very nicely, but it doesn't have this enormous mapping costs that you have with a qubit. Quaternions are another way that you can have some interesting mappings, although that gets a little more complicated. But just this one simple representation kind of gives you what you're going with that. Addendum on both. Neither of these gives a good representation of entanglement, and that's something I would love to see a better representation of these things related to entanglement. I think that's possible too. If you want to show entanglement, you need pairs of qubits. You can't do it with just one qubit, but you could show, I think, more directly some of the relationships between the qubits. So IDA analysis says block spheres, not a good idea. Probably just wasting a lot of computation. It's not that they don't work. Now, that's very important. It's not that they don't work. It's just like you've added so many bells and whistles and fancy things and fun things to explore that you're not really getting that. Condensed matter continuum, we live in a condensed matter world. It makes the Euclidean definition of infinitely smooth points, of infinitely precise distances, of particles and waves, all very solid, very real. And I would point out that waves, often people talk about quantum duality in terms of waves are quantum, particles are real. No, that is not what happens. Waves and particles are both very classical phenomena. They are a dual way of representing something that's going on that we don't really get very well even now, because the waves have a particle representation, the particles have a wave representation. So the very fact that you're saying that one or the other is quantum, you're missing the point. It's that duality around the Planck constant, that ability to switch back and forth, the Fourier transforms. That's where you really get some interesting things going on. And I don't think we have a good model if we casually think of waves as being the mysterious part. Waves show up when you go in through solid matter. In distant space between galaxies, you got to be a little careful about thinking of a photon as a wave. There's something much more interesting going on that is very obedient to the speed of light, but not what we think it is. So another thing I bring out, I will continue to bring this out because too much has been written about observation being incredibly complex phenomena if you simply go to the idea that any form of acceleration collapses whatever we think of as a wave function. It just makes things so much easier. So the quantum phenomena that we witness on a regular basis is nothing more than getting rid of the bumping, which is heat is one of the sources of bumping. And then we see this mysterious effect that is just a remnant of an environment, classical environment, in which everything's involved, is constantly observing itself. Does a proton know where its electron is in a hydrogen atom? Of course it does. Does it forget where the electron is? No, it doesn't. That hydrogen atom will persist for billions of years. How is that different from observation? It says that now the location of the atom, that's a whole different issue. The location of the atom, it could be all over the universe. It could literally have a wave function bigger than the universe. But in terms of the proton and the electron, they don't forget where each other are because they're always bumping into each other. Forces do that. So it's a different way of looking at it, but making observation mysterious is really causes, I think, damage because we don't need to make it mysterious. Um, I'm going to suggest, I don't know if this is a good word or not, but I'm trying it out. Instead of infinitesimals, and I mean very specifically that an infotesimal is the same concept as an infinitesimal, but funded by real mass and energy that gives it reality at some scale, and it is not infinitely small. It is very small, and the size can go smaller and smaller and smaller depending on how much energy you fund it with. So if you've got enough energy, you can make your infotesimal incredibly small. That's why we have particle accelerators. We want very tiny infinitesimals. We want a little analysis of the electrons that we're shooting or the particles we're shooting that are very compact in their definition of space. So it's just it's a way of putting a limiter on this and saying that, yeah, this is the real mystery, is that there is no such thing as an infinitely small anything, because including those irrational numbers, because they all cost infinite energy. And they all cost infinite computation if you try to make them real, even in pure math. So infinitesimals top down, they're energy dependent. They define space relationships. Remember I was saying that maybe we're looking at space the wrong way. It's really a set of relationships, some very low energy between particles, and then they present themselves as three independent axes that we interpret as space. That's very different from saying there's some magical fabric that just happened to be there. I always love that. How do you get something as complex as space-time just happened to be there? Oh yeah, it just happened to be there, and some grubby matter came in and started doing stuff inside of it. Why? The structure, the mathematical information structure of space-time is so complex that the idea that it just happened to be there, because obvious. No, it's not obvious. It's derived from Euclid and everybody else based on how matter behaves. So this is not a finite, granular, discrete universe. And I want to emphasize that because people say that there's a discrete universe and it all just breaks down into little bits. No, that actually increases the problem. That does not help. Infinitesimals simply create detail in keeping with what you got. If you use an infinitesimal approach, then you can have things like gamma rays that stretch the limits of special relativity, and everything works perfectly because it's all dependent on how much energy you use to fund it. You got a high gamma ray, you're going to be creating space-time out to gazoo for that particular entity, and it's going to be perfectly precise. There's no cutoff. That's different from a granular or discrete universe. Discrete universe has all sorts of problems and has cutoffs, and you can't really make it relativistic. So smoothness emerges due to dividing up in energy. That's the other thing. Those triangles in the Leibniz model, they get smooth simply because you run out of enough information to get the second derivative. You run out of information to provide the curvature. You wind up with only enough energy, just enough energy to give a slope. So in that case, the smoothness emerges naturally as a function of how much energy you have. Analyses, this is what I was saying earlier, all of our analytical methods, they need to look a little more closely at this information energy issue. They really do. And Taylor series are, in some ways, I think, just more fundamental than some of the other things. The Taylor series inherently seems to be kind of recognizing this, and it's one of the reasons why it's such a powerful method. So if you look at it in terms of impact, if you do an infinitesimal analysis, you have to discard continuum analysis. Even this is remarkable. Even the real number line falls victim because you cannot have a real number line without imposing infinite processes that never end in any imaginable real context. So again, I can make any program I want. I can point out that there is a limit to that program. But if I say that I actually have that limit, that's a very different statement. I do not have pi until I have all the digits worked out, and I can't do that. I can say that there's a system that exists as a result of my program, but that's not the same statement. So if you go with infinitesimal analysis, all forms of real analysis are deprecated. What do I mean by deprecated? I don't mean it's thrown out. They work. You don't discard them, but it says that you have to be more careful. You have to be careful on how you're limiting what you're trying to do. I mentioned signal dispersion. I think if you go into an infinitesimal analysis, phenomena like just dispersion of momentum dispersion in particle physics, the fact that a particle just kind of breaks apart, can be reinterpreted a little bit differently in terms of information and the information density. So there's some interesting things going on if you bring information explicitly into some of these analyses. Um, I do think that mathematics, if we say Euclid was a little too early by 2.5 millennia to know about some of this stuff, but given modern physics and what we know about the absolutely intransigent, I love the speed of light limit. You know, people talk about spooky action. There is a spooky action, but that spooky action is the transformation of space-time when you actually finally get a signal. Uh, you know, uh, um, it's the velocity of c is related to how fast you can transfer information, and how fast you can transfer information, and whether you have different rates at which you transfer information creates an enormous amount of interesting complexity in how the universe can work. On the converse side, if you just ignore any kind of signal dispersion, you say everything in mathematics goes everywhere, everything everywhere all at once, is it really surprising that you get paradoxes? Is it really surprising you get contradictions? Because of course you are. You're elaborating competing processes, none of which can have real resource, none of which can go to infinity. So to signal dispersion analysis, I think there's something interesting could be done with that. Summary: universe is neither continuous nor digital. It's something a lot more interesting. It is infinitesimal. It is capable of elaborating things to whatever degree you got the money to pay it, money being the matter and the energy. And you will always find it smooth, as smooth as you want it to be, if you can pay for it. If you can't pay for it, you wind up with something more that uncertain, and you don't have a lot of trouble coming up with quantum mechanics in a world that's dominated by that kind of effect. Because when you reduce the funding enough, when you get a particle light enough, like an electron, it no longer has the capability of having a well-defined location. So it's a different take on the uncertainty. Now, the whole thing about how it collapses, that's an interesting issue. That's a different one. But in terms of why it looks fuzzy, really, if you use an information analysis, it kind of fits. It's kind of saying you got below the pixel limit. You don't have enough information to fund it. The pixels are very mutable in size, but there's a pixelation effect on that. So my suggestion is that we take non-binding relationships, especially actually because this again is the long-range version of the Casimir effect. So I think Casimir was onto a really interesting point when he said that in 1998, almost like a final confession, one of his final talks in the final sentence. He says both of these are real and they're the same thing. Now think about that. That is just fascinating because he's saying that, yeah, this thing about how space-time works seems somehow to be connected to this thing about how mass and energy works. And he was a solid state physicist, so he could see that. And he didn't he's looking at something. I don't I think he was frankly saying, like, I don't get the connection, but there's something there. And I think he was on to something with that we lean to look at QED in terms of QED funded by bonding, by very diffuse bonding energy. So start with these non-linear bonding relationships as a way of taking a different whack at how space-time works. Stop discarding low energy as relevant. And I'm going to take a whack at, you hear the statement, classical, math has to be fundamental because it's so unexpectedly predictive of physics. That is true. But you've got to take into account the fact that the maths that we use were derived from physics. And the physics concepts they were derived from are incredibly complex. Space-time is not a simple concept. It does not have a simple instantiation. Hidden beneath those simple statements are things like duality of spaces, inherent wave nature. None of that is covered in the classical maths. So if you base everything on these classical maths, and by that I mean concepts as simple as an absolute point, then you have to be careful that you will get predictions and you will find extremely interesting math, but you're probably going through a lot of noise that really, really, really is not that relevant to it. And that noise shows up whenever you have infinite information densities that you don't have enough funding for. And with that, I am done.
Uh, in your part of your conclusion, I noticed Otis has a comment on YouTube. He said, but the very definition of continuous is the same as space, can be broken up into smaller infinitesimal parts. I don't see how your theory is in conflict with how the universe being continuous.
Uh, if you phrase it that way, I don't see a conflict either. I'm saying there is continuity, but the continuity has a cost to it and that it's multi-scale, because if you have a relationship between a particle here and a particle on the other side of the universe, that's a pretty remarkable relationship, and it does imply there's a continuity to it. But what I would not go along with is the idea that the continuity extends below the level of ordinary matter and energy. So, for instance, you have ideas like multi-universes that are based on, a point has infinite numbers of different universes contained in it. I wouldn't go with that at all. But I say within the universe we have, there's a lot of smoothness, and we just need to look at the smoothness a little bit different angle so we don't inadvertently make infinitely dense information that's not there. That's the thing I worry about is when we assume levels of information that we have no physical evidence that that's possible.
So do anyone has other questions?
Small query. Harry, thanks for your presentations. Very interesting and always learning something. I just query about the infinitesimal that you've been talking at the beginning of your presentation, particularly the concept of point as a spherical entity. I wonder if it is correct to define it as a spherical entity with zero radius or an infinitesimally small radius.
I think that's very much what Euclid was going for. He was going for spherical with zero radius. He was trying to eliminate any kind of orientation issue with that. He said, it should, which makes sense. He was trying to capture the concept of location, try to capture it as precisely as he could. And again, the whole point of the presentation, where I'm going with this, is that we need to think of issues like that as being convergent limits, including starting with the concept of a point, because his concept of a point is not trivial. It's not it seems trivial, it seems obvious, but that's because we have a classical universe all around us, and the idea of shrinking something down and getting more precise is very intuitive to us. But if you go out into quantum mechanics and you go out even a little bit out into space where matter is more sparse, wow, that idea changes real quick. And the only precision we have is what we carry with us because we're so intensely classical by literally by our nature. So yeah, I think he was going for that idea of zero, but really the point of my presentation of this is let's kind of rethink that idea about how close you can get to zero, because we know quantum mechanics doesn't allow it. And Euclid could not possibly have known that. So when we casually use those ideas, we need some caution.
But if you question this idea of zero radius, then one may question also the concept of zero as an absolute uh, uh, entity. Is it really zero, an absolute entity or is also a kind of infinitesimal entity?
And I think you would have to do, and in fact, actually debates about the nature of zero do focus on issues like that. Is zero a limit? The fact that you give different definitions for dividing by zero, zero by zero, you can get two different definitions for it depending which limit you use. So zero is an interesting concept. It's a non-trivial concept. And in terms of the kind of framework I was just talking about, to be honest, you would not have an absolute zero on anything, because the moment you have an absolute zero, you're outside of this universe. You've pushed yourself out from the boundaries of like these very diffuse relationships that define how particles work. So again, you can always define these mathematically as abstraction. There's nothing wrong with defining continuums and that. The thing you have to watch out for is saying, and what does that mean when I actually try to implement that? And where do I go with the various infinities I get with those? So yeah, I would say to some degree that I'm suggesting that in the finite universe, you can get very, very, very close to zero, but you would have some trouble getting an absolute zero. It's a kind of a net positive. Where you would get to zero is if you get into concepts of total annihilation of particles. Then you could start talking about some real zeros.
So thanks for your answer.
Thanks.
Appreciate.
And I noticed Otis had a question on YouTube. So the waves themselves are discrete. So no need particle to make energy discrete. Did I get it right?
I didn't quite catch the question. Could you repeat it?
Sure. The question is, so the waves themselves are discrete. So no need particles to make energy discrete.
You don't need particles to make energy discrete. I'm sorry, I have to admit, I'm not sure if I'm following the question. So could the person come online, maybe phrase it verbally?
Oh, this is on YouTube.
Oh, it's on YouTube. Oh, it's on YouTube.
Yes.
Okay. Yeah, I'm afraid to try to answer because I'm afraid I may be misunderstanding the question. So maybe if they could do another iteration of it, I could try again.
Sure. Maybe Otis can rephrase the question on YouTube.
Yes, if you could, because it sounded like an interesting question, but I'm not quite catching the gist of it.
And Robert has a question. What is energy in your conception?
Ooh. Well, I'm certainly putting mass and energy as very much an equivalence. So you have the absolute conservation of mass energy. And the honest answer is I have no more idea what energy is fundamentally than I think most people do. It is something we see in the universe. It is a measurable quantity. It has the ability to change things. But that's a very interesting question. And frankly, now that you've asked it, I think I'm going to have to think more about that, because that is an interesting question. But I don't know a good. Yes, someone's talking.
Can you hear me?
Yes.
Yes, question. Yes, the question.
What struck me was how fundamental the concept plays in your conception. I'll call it Bollinger theory. You question, you reinvestigate, you reformulate very fundamental ideas like points, lines, the nature of the vacuum, which is fascinating. Yet at the heart of this, or at least lingering around that, almost like a cloud of the picture in QED of clouds of charge or clouds surrounding a particle, screening clouds. That conceptually, energy is sort of acting like a screening cloud around all those concepts. And so I was wondering if you had reinvestigated, delved into what you regard as maybe a reinterpretation of what energy is.
Well, one of the things I can answer that to a certain degree, which is this: there are two constants in the universe that I think are more inviolate than current physics seems to think, which is, to me, is just odd, because those are conservation of mass energy and the speed of light. And I would assert that if you take those both incredibly seriously and say that energy is never, ever, ever violated or lost, it's distributed. And by the way, that is
not momentum conservation, for example.
Well, momentum is very different from energy. Momentum, you can create any number of pairs of energy. You can, in fact, I think that's one of the most fascinating mechanisms of the universe. I once did a little paper about how in principle, you could use one green photon reflecting between two reflectors to create two locomotives worth of momentum. And this is something people miss about momentum. You can create arbitrarily large amounts of momentum, especially if you use high mass objects, using very small amounts of energy. And so momentum conservation, total momentum conservation is an absolute. Magnitude of momentum is not. Whereas in the case of energy, total energy is an absolute as far as we can tell in our universe. And I'm a dual
A
universe.
vector and a scalar. Yeah, true.
Say that again?
Difference between a vector and a scalar, that's true. Of course, in relativity, the mass energy is regarded as a zeroth, usually taken as a zeroth element of a four-dimensional momentum vector. So they're not separate concepts, at least relativistically.
Yeah, and in fact, I would think the more complete representation of energy is that it too is a vector. I not only don't have a problem with that, but I think we need that kind of perspective about the space-time. I think you need to go to higher dimensional space. And again, I'm a dual universe person, so this is the Boyle and Turok are the best, great papers. Boyle and Turok have explored this dual universe concept in more depth than anyone I know of, and more mathematically. So just enormous respect for their work. But I am explicitly and unapologetically a dual universe person. And things like energy, when you take those two universes into account, I would say you get a real zero. You can actually go back to an actual null, not just a virtual null. The reason that we have a universe at all seems to be this invention of this concept of time that messes things up. They get like two pieces and they suddenly say, like, I'm going to go this way, and this one says, I want to go that way. And they separate for a while, very long while. But I think this idea of time is just critical to this creation of these entities. But once you're within that one universe, in our universe, the energy is the total energy just is extremely intransient. And the reason I emphasize that is more for the algorithmic side. I think some of the things that we think of as fundamental algorithms are actually being driven by conservation. I think if we looked at conservation, the speed of light conservation, speed of light more carefully, we'd find that some of the algorithms that we think are more fundamental are actually emerging from that. So it's kind of reverse of Noether's theorem. They have the continuity produces the conservations. I repeatedly flip that around, saying, no, I think it's the other way around. The conservations are creating the continuities. And when I talk about these infinitesimals, that's kind of where I'm going. I'm saying that, yeah, there's something very interesting going on here, but we got the direction a little bit backwards.
Well, that's an interesting idea. Theorem is two-sided, but yes, most people do take it one way, then not the other. That's an interesting concept. The dual universe, I don't believe I've heard of that conception before. I don't think I've heard of that one. So that's actually new. Would you say Boyle and Turok, I think you say.
Oh yeah. Yeah, I sometimes call it Retton's theory. It is, as far as I know, it's my own. I always look for priors. I haven't found one on that one, but I just know there. I spell Noether backward and you get Retton, but Retton's theory it's just swift flipping around. Noether was very much a continuum. Infinite differentiability, perfect mathematical continuity. And if you notice everything I just said was kind of saying, I think that's a bit of an illusion, because these things don't have good examples in the universe that we actually observe, which always should count, because that's the only formal system that we really have. We can invent formal systems, but the only one we have that actually works is what we observe around us. It's an inspiration for many things. So yeah, I call it Retten's, however you pronounce her name backwards, as an attempt to give respect for the fantastic work she did. But I would reverse it. I would reverse it. And I think that's could be an exploration in a really interesting exploration path. Is say if you have absolute conservation and you have this idea of very easy wave collapse just through any form of acceleration, any force that acts on something, I think it could pop up some interesting different ways of looking at some standard equations. Somebody is coming in at this late of a date. Other questions?
Yeah, Otis has another question. He rephrased it, but if you are saying that since the waves don't have to be infinitely broken up into infinitesimally small parts, then there's no need for the existential particle to explain away the photoelectric effect. You are saying that space can be broken up into infinitesimal parts, but waves can't. Did you get it right?
Okay, so the question is partly about the photoelectric effect. So
Right, the question is on the chat.
yeah, which I can't see at the moment. That's an interesting question.
It's a very long question. It's on the chat.
Yeah. Oh, wait. Okay, here's chat.
The latest message on the chat.
Okay, let me look down. So this is from
Otis.
Otis.
Is
Okay, let me spend a second reading it here. What I'm saying is that everything that we see that looks like a particle or looks like a wave is equally, both of those are interpretations of a single entity that is conserved. So you can have a classical example. You have an electron that looks like a particle if you put it in the right circumstances, or you can have an electron that looks like a wave if you put it in the right circumstances. A band electron looks really, really like a wave. And people who think that quantum wave mechanics doesn't affect us at room temperature, you need to look in a mirror literally, because the fact that you're seeing yourself in that mirror is very much electron wave mechanics in action. You're seeing that the top level of the Fermi level, those electrons are hot too. They're actually X-ray hot. If they collapse back to their ground state, it would kill you by standing in front of a mirror. So they're very real wave effect electrons, and ordinary examples around us all the time. But oddly enough, the particle version of the electron is the harder one to get, because you either have to bind it into an atom, which you get an orbital, or you project it at a very high velocity through some medium like a cloud chamber. And a cloud chamber, again, I have this very, very simple definition of observation is if you bump something, you observed it. There's no great philosophical mind going on this. This is really simple stuff. So every time an electron goes to that cloud chamber, it bumps. And it looks like a path of a particle going through the cloud chamber. But if you take that cloud away, I guarantee you don't, well, I don't guarantee you, this is just scientific fact, you don't get the same behavior. It goes back to being a wave. And that says this duality is just profound. And if anything, the harder side of duality, I think the reason we exist is that matter found a way to constrain that wave behavior so that we have things like atoms, that we have things that suddenly exhibit this ability to relate to each other. So I think if we want to see how reality emerges from these dual spaces that are the only kind of spaces anyone has ever seen, and they're all wave-based, then look no further than the asymmetry between momentum space and regular space. Momentum space is asymmetric and has a minimum. So the farther out you get in momentum space, the more intense the energy becomes. Real space, location space, is completely smooth over that entire thing, just like I was talking about. And that asymmetry seems to be deeply related to why we can exist at all, why we can have this kind of particle thing, because the momentum space representation kind of breaks down for classical objects like us, which is the whole reason why Euclid focused on the location space. That's what he saw. And just some fascinating issues with that about everything is dual. Everything has this double representation of two waves, and why that is, it goes something deep on where this is all emerging from, and I don't think we understand the full details, but I think there's potential for progress, especially if we focus more on particle behavior and say, how might that help exhibit the space-like capabilities, such as through long-range Casimir effect. I don't actually, existence of particles. When you do a photoelectric effect and an electron comes out, it's not a particle. The instant it goes out, this is the old dispersion relationship. I mean, this is very well documented. The minute that electron leaves that particle, unless it's going through air or unless it's going through a medium, it immediately becomes a wave again. Every time you locate a particle that's not a classical object, it instantly wants to become a wave again. The more you localize it, the more it becomes a wave. It's just this bizarre relationship. Particles are hard. They're hard to do. When we assume them as a given, we're destroying we're destroying more than half of the potential for insights into what's going on, because we're assuming something that, first of all, doesn't really exist in the physical world. We don't have point particles. We know that, not energetically. But particles are just a profound and fascinating kind of illusion of this very wavy universe, is how I would put that. So yeah, you don't need a particle when you do photoelectric effect because it immediately becomes a wave. Other questions?
Yes, Otis has another question. So a wave turns into a particle and a particle turns into a wave? Depends if it bumps into another object?
Yes, and I remember when I first read, Feynman has a beautiful little piece about this, how if we could see about 10 times better than we do, we would know that photons are particles because we would see them. We would see them go boink, 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 boink. And they've done statistical studies in which they've shown that really is true. People actually can just barely, almost unconsciously, detect whether a single photon has arrived and hit their eyeball. So the qualification that I always put in this is we need to stop thinking in terms of particles and waves and think instead in terms of constantly constricting what we would think of as a wave, because you never get to the particle level. And the interesting phenomena are the ones where a wave turns into a much, 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 much smaller wave. So you get a photon from across the universe, it pops into a single retinoid or one of the photoreceptors molecules in your eye, and retinol, I think that's but it pops in there. At that point, it still does not become a particle. It simply becomes an energetic version of that molecule, which has a finite diameter. And what you find in every case for electrons, for things we think of, and even for atoms, for particles in some of these double slit experiments, the particle nature is the more difficult thing to get and always seems to have a finite limit. Now, if you lump enough stuff together into a massive ball, we don't see that anymore because everything is observing each other so much that the baseball looks like a baseball no matter when you look at it. It still stays a baseball. If you float that baseball into completely empty space without a photon in sight anywhere, then even that breaks apart. And the ball stays a ball, the baseball stays a baseball because it's observing itself, but its location to the rest of the universe gets lost because the universe is no longer observing the ball. So these observation relationships are just, to me, are just fascinating because it doesn't take much energy to observe something. One photon will do it. You can have an elephant floating in space. You zap it with one electron, and all of a sudden the universe knows where it is again. So that's this asymmetry in observation, I think, is one of the powerful features for why particle illusion seems so strong. So I would agree that what really happens is the observation, the degree of particle likeness that you get is always proportional to the amount of energy used in the probe. So for instance, if you have electrons going through two slits, Feynman covers this beautifully. If you have electrons going through two slits and you put an electromagnetic wave that's larger than the diameter, the distance between the two slits, you still have quantum electrons. You still can't tell which slit the electron went through. But if you get the energy high enough to be smaller than one slit, suddenly the electron has position. Now that doesn't mean it's a particle, because it's still very much a wave when it comes out of that slit. Absolutely a wave. It's not a particle. That's a mistake people make, and think suddenly it just becomes like a particle and sails. No, it doesn't. It becomes a wave again. But if you do that, the amount of localization is directly proportional to the energy of the photon with which you nailed it. And that is saying something interesting about observation, that it actually has a quantifiable side about how particle-ish can we make something given a certain probe. And people tend not to talk about that because, again, the particle perception is so deep in our training, the idea that everywhere is hiding a point particle. And yet there is no physical evidence for that. There just isn't. And people who work with this stuff, excitons and doing like metal, they work with solid state physicists, know this very well. The neutrons do not behave that way. Electrons do not behave that way. Highly energized excitons do not behave that way. They all behave like waves that then get constrained. So there are components of the physics community who are extremely aware of this because it's their daily job. But I think our casual perception is we always believe this particle idea that is somewhere there's a lurking particle in there. And of course, if you go for the pilot wave theory, that's explicitly 100% stated as being the proposition. I am not a particle wave person because it's a useful technique for analysis. I mean, my gosh, look what Bell did with it. Bell came up with this theorem because he used it as an analytical model. So it's a beautiful model for doing it. But what you've really gone to is two infinities. You have an infinitely precise wave and an infinitely precise particle. And I'm saying like, no, it's something that both of those extremes are not quite getting it. So photon has a size that depends on how long it's been sailing through space and how many companions it has. If you have a laser beam, if you have the interesting thing about laser beams, if you take a little laser, you put it through a giant telescope and you send it out there in a wavefront that's like 3 meters wide, it will stay tight for an enormous amount of time. And that's also true for a single photon. A single photon, if you put it through that same thing, and that's bizarre. That's bizarre. So you take a single photon, put it through a gigantic concave mirror telescope in reverse, bounce it off that mirror, and it will stay precise for some incredible length of time. One photon. Now, think about that. I just love that, because how did that photon get that much information from that mirror that's able to do that? It's the photon size in that case is similar in diameter to that mirror in a very real sense, because without that diameter, it wouldn't be able to behave like that. It wouldn't be able to receive it with 100% certainty at some receptor. Whereas if you do it that way, you can. So yeah, that sounds like a size to me. It says like the bigger the size is, in fact, the more precise the photon gets. But interesting, just fascinating stuff on what you can do with a single photon. How much information they do. And also, I think it gets into the issues of entanglement. I addressed that some in my last talk. But a single photon can, in a sense, record an unbelievably complex image, but only in the sense that it records one tiny little piece of it. You don't know which piece it's going to record. So it's weird. There's a weird relationship there. A lot of fun. It's very fun and relevant to things like quantum computation. Other questions?
On this question of particle wave duality, just been a bit heretic. Is it really duality, or we just talking about just particle and wave is just a manifestation of a particle in a particular media during its trajectory? So imagine when you throw a piece of stone in a pond and you see the waves, water waves, that's a manifestation of the stone which is thrown into
Yes.
the medium. So what we're calling wave is just a manifestation, an energy manifestation of the particle. The particle is still there.
Yeah. In fact, I like that analogy. I've even used that analogy trying to explain holography to people. That's stones in ponds, especially multiple stones, make a great way of explaining how holography works. So that's relevant to the, for instance, to the LLM community, the large language models, because their models are essentially holographic. They don't call it that, but it's essentially the same behaviors. So you get these ideas that you throw it in there, you get the waves. The difference is this: when you throw in the electron disappears. It becomes the waves. That's the difference in the analogy. So when you have an electron go through a tiny hole, all you find is a wave behavior. Now, the reason it gets, and this is the mystery that goes back a century, and upset Einstein and Born was the one who came up with it. Said, well, it seemed like this wave turns into a probability of finding the particle or a more condensed form of it. But you can't discard that until that happens, that thing behaves like a wave. It reflects. If you look at neutrons going through graphite, you don't study those as particles. You study them as waves. If you try to study them as particles, it doesn't work. You're seeing this screen right now. If you use a particle model of a photon, that wouldn't happen. The photon would get lost in the proteins of our eyes. We would all be blind. The only reason that we can see individual photons is because each photon essentially encompasses the entirety of our eye. And that's not just an effect of the photon, that is the photon. The photon is the thing that is somehow encompassing all of that information. So there is a lot of power in the particle and wave duality model. And I point to John Bell as a marvelous example of that. He was a dedicated particle wave dualist. And he was able to analyze problems that no one had analyzed correctly before that. So he made good mileage with that model. There's other cases where the particle wave model definitely can get you in trouble. And I remember Feynman definitely was not in that category. Even though it's interesting, Feynman believed in particles, absolutely believed in particles, but he knew that there were problems with the dual model. He couldn't, he avoided it carefully. So multiple ways to look at it.
But it couldn't be a question of our current technology in terms of instrumentation, the resolution of our instrumentation, the capability of going as small as possible and being able to zoom as much as we can. That could be actually the barrier to our understanding of this duality that we're debating.
You can certainly make a photon to be extremely small. And some of the more interesting forms of microscopy do exactly that. There's ways of constraining photons. I can't remember the name of the tech. There's an interesting technique where they essentially do just that. They shrink the photon down so that you get better resolution for it at a given frequency with that. Again, I make no bones with it. I'm a deeply dualist viewpoint that I think either the wave or the particle doesn't match what we actually see, because we just don't see the particles. What we do see is unbelievable shrinks in the size of the wave to do that. And I said there's some question here. Now actually somebody said, okay, Otis, I think that was you again. It's not going to be observed by the mirror anymore after it bounces off of it. When a photon bounces off of a mirror, it has been observed in two senses. The photon imparts momentum that is measurable to the mirror, so that's a bump. That's a detection. But if that photon originally was one coming from the sun, the diameter of the photon's wave is absolutely enormous unless it went through a reflective, some kind of special mechanism. So the size of that photon in the case is just gigantic. And once it hits that mirror, it has suddenly been localized by many orders of magnitude. And how is that different from an observation? It really isn't. We do the same thing in our eyes. We just do it with proteins at the scale of our retina. But it is an observation. The mirror will not see it anymore. And this would be a different topic to get into. But But I do believe there's an entanglement relationship with that mirror because the photon doesn't have enough energy to record that mirror's shape. And yet, if you set it up right, it will follow the path that that mirror directs it on to a T, to where you get 100% certainty of finding it. And yet it's still a wave for all the intermediate parts. If you test in between, it doesn't do that. So I think we're getting a really interesting relationship. And it's not a standard. If we get deep into the entanglement stuff, especially our usual concepts of space and time, just aren't going to cut it in terms of explaining it. You can't transmit information faster than speed of light. But there are things going on in the mechanisms beneath that certainly seem to be doing things that, as far as they're concerned, the particles are just sitting right next to each other. So you get a photon that goes through a galactic lens, it still has information about that galactic lens. How is that possible? That seems bizarre. And yet if you get enough photons coming through, you say, oh yeah, every one of them recorded a little bit of signal from that gigantic lens. Other questions?
I noticed Lido. Okay, let me see my notes. Lido has a comment. He said, I remember a lecture from Leola Suzuki where he generalized physics to 1 particles, 2 fields, 3 forces, and each of those seems to have a physics interpretation of energy. And can Lido unmute? There you go.
Yeah, thank you. What sometimes the hallmark of a good talk is when you have nothing to say. And that's when the information you're really contemplating what the person says rather than a refutation to what they're saying. Anyway, it's an awesome talk. It really makes you think, especially entanglement and stuff. I think the question of energy came up, how we interpret energy. And I just remember an MIT lecture from Leonard Susskind where he drew on the whiteboard, particles, fields, and forces. And ever since then, it just stuck, because when you think of physics, those are really at the heart, particles, fields, and forces. Like everything's broken down into those concepts. And I think, I'm not an expert in physics, but each of those analogs has an equation for energy, in the term of particle, field, or force. So I just added that in as a discussion.
Yeah, and the modeling of energy, the way you've represented energy using a Hamiltonian is a very space-time way of doing it. So you get the variational methods that Feynman used. That's a critical issue in how you do it. Leonard Susskind is a very good teacher. And incidentally, I have this little thing. In my mind, no one's ever won a Nobel Prize for string theory. Because string theory, first of all, I don't think exists. However, if you go back to the original meaning of the word string theory before they turned superstrings into string theory, because that was a jump of 20 orders of magnitude, the original string theory was actually a description of the strong force behavior like a string. And the strong force behaves very much like a string, and it vibrates. And this produced these resonances. So you have an excited version of a proton, an excited version of a neutron. Very mysterious back in the 60s. Leonard Susskind wrote a paper in which he was the first one, through a rather complicated mathematical argument that was not obvious. He figured out, said, this is like a rubber band. This is like a vibrating rubber band. To this day, and by the way, I disagree with almost everything Leonard Susskind said about superstrings. I still think he should have gotten a Nobel Prize. I still think he should get a Nobel Prize for that. He figured out the existence of the strong force and its behavior before anyone knew there was a strong force. So why in the heck didn't he get rewarded for that? And I still don't understand that. I got that paper and I'm just looking. It's got a little note at the end. It says, this is like a rubber band. This was a deep insight that he got to by using mathematics. Now, if anybody who knows just how much of how antithetical I am to superstring theory and what a proponent of superstring theory Leonard Susskind may find it very surprising to say that, but I don't care. I mean, the point is he did something no one had done at a time when nobody knew. This was 1969 and anticipated and actually quantified through a nicely done but complicated mathematical argument. He found something that no one had noticed. So someday I'd like to hear a story on why he wasn't acknowledged for that. I still don't understand it. So, but that's the real string theory, the quark orbital string theory, because that's all they are. They're quark orbitals. Quark orbitals behave like strings, like vibrating strings. Then they elaborated that to an unbelievable degree in a direction that went towards infinite information anywhere, all that. And you just saw my talk and what I think about that. Infinite information is dangerous. So thanks, Lida.
Yeah, thank
I
you.
liked your talk last week.
Thank
I
you.
like, yeah.
One thing you mentioned in that talk, and I've been pondering it ever since, and maybe you might be able to share a little more enlightenment, is the idea of entanglement. Um, you know, I try to get a hold on the meaning or definition or how you demonstrate it, and it just seems so elusive. Could you add maybe a little more, just say a little bit more about entanglement, what it is, or however you feel comfortable, but just shed a little more light on the idea of entanglement?
The only thing I can give as an insight to it is I think we have underestimated the level of entanglement to an extraordinary degree. We tend to think of entanglement as just two little pairs and little things. And this is why I keep going back to that example. One photon, 10 million light year galaxy Einstein lens, goes there, winds up in a telescope on Earth. So you find out one little tiny bit of information about where the lens is located and what's behind it. Collect a few thousand of those, suddenly you have more detail. But every one of those photons, in some sense, knows the shape of that galaxy cluster. How can one photon know the shape of an entire galaxy cluster? And that's why I think we're underestimating the importance of entanglement. I think in some sense, entanglement must be involved with that. And that's not the usual representation of entanglement. There's many good representations, but I think we tend to make it too narrow. And the way to explore that, though, would be with photons, because photons are an extremely easy room temperature quantum effect that marvelously demonstrates just that strange relationship between small packets of energy and enormous levels of detail, that the more you fund it, the more energy you put in, the more photons you get, the more details you get. And yet, each photon has to have, in a sense, its own image of that original system, or it wouldn't land in the right spot. So, but I would agree with that. Entanglement is incredibly important, and if anything, I think we underestimate it, because I think it's part of the deeper infrastructure of where space and time emerge from, is from the entanglement. And if you have observation going all over the place, and if acceleration is observation, those galaxies, in a sense, observe that photon to some degree. So this idea of simple, easy observation through forces, through to what we just call a potential, really, as interpreting potentials as observations, I think is a powerful analytical technique for understanding entanglement better. Most of the models we just kind of cheat. When Feynman gets cases where you have the whole lens that the photon goes through, he would talk about a potential, and for years I always thought that was fine. But then the more I got to think about it, I says, isn't that kind of a cheat? Because the potential that he was talking about disguised an incredible range of problems about how the photon was interacting with that entire lens. So potentials are an easy way of summarizing some effects, but they don't necessarily explain. For instance, with a potential model, you may miss the fact that the photon leaves a little bit of momentum when it goes through a lens, and the amount it leaves may vary. There's a famous paradox, the Abraham Abraham something paradox, about how much momentum you deposit in a lens when a photon goes through. It's still considered unresolved. People have different explanations, and that would be, for instance, an example that absolutely should be looked at more carefully in terms of entanglement relationships. If you didn't observe it any, you won't get any deposit of momentum. If you do, you do. So I think that could be an explanation for that.
Thank you so much.
But thank you. Anyone else?
Oh, Ron has a comment. Oh, go ahead. Yeah.
On the question of entanglement, some people have been talking about the cosmic electromagnetic filaments which originated from the Big Bang event. I just wonder if this electromagnet remaining filaments which connecting galaxies and so on, if they influence the entanglement.
I think something really interesting is going on with all those filaments and the large scale structure of the universe. And apologies for saying this, but if you took Einstein's general relativity and predicted what the universe would look like, which people did, there's not what we're seeing looks nothing like that. Nothing. And of course, we came up with dark matter and all the other reasons in order to preserve that. But there was nothing predictive about general relativity for saying that the universe would turn into be giant gyrating filaments that spin in huge circles and then carve out little pieces of space, and sometimes they form blobs. You get this, it looks more like a taffy pool than something that would be created by gravity. So whatever's going on with these filaments, I think it's electromagnetic is part of it. And again, you notice if you think about what I've said in this talk, I've said that electromagnetic may be a lot more important for understanding space-time itself. So that there's a general field of very, 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 very weak electromagnetic that helps define relationships in different scales. So I think these filaments are reflecting some aspect of that. And a personal suspicion is that if you stretch the gravitational model too far, it's like taffy, that it actually starts to break down. And you start getting gigantic cosmic voids that are where it's just not enough matter anymore to support it. And the thing just sort of like pulls off and actually goes in other directions. So that's usually explained in terms of dark matter, but I think it might be fascinating to analyze issues like that in terms of space-time itself, saying that, yeah, maybe space-time's a little bit wonkier than we thought. And I will eventually be giving a talk on some aspects of where space-time really just can't be quite what we thought it was, because it has some complexities that show up in special relativity. Is what I'm looking at right now, that you have to take them into account or you don't get the right predictions. You can wing it and you can say, well, in this case it did that, but that's just it. That's just winging it. We should have precise predictive frameworks that say exactly what happens when you have a twin paradox without any hand waving. There shouldn't be any hand waving in this stuff. It should be a precise prediction. And to do that, we have to modify our understanding of space-time a bit, and which is something I'll get into. If somebody's seen my tilted block diagrams, I got to get back to those. Those are just delightful. It's a slide rule for special relativity and gives precise answers. And that's just fascinating, because you can just tilt a block on its side and give you the full range of answers with proper limitations, proper discontinuities depending on the direction of acceleration, proper counting of the clocks. And you can put it in equation form, but the block just is so much more intuitive in terms of saying what's going to happen. So you could literally build a slide rule that would calculate with more precision and more data what would happen in a given situation. So, and I am wandering at this point. Other questions?
Yes, Monty has a question. How does lambda fit into the model?
Lambda, or you're talking about the lambda for, right?
Monty,
drawing-
can
Speak
you?
from the poet with cosmology. The poet
The
with
lambda in
lambda
cosmology is, yes, remind me, the lambda in cosmology, though, is the which constant? Sorry, I'm drawing a blank on lambda right now. How does lambda, what?
Well, the lambda behind dark energy, the theoretically behind dark energy and such, it's Einstein's parameter that
Oh,
he
you
plugged back into
okay,
if I'm remembering correctly.
Einstein's constant and something like that. Um, honest answer is no idea. Lambda, well, that's not entirely true. I think we're in a naturally dispersive universe that is trying to annihilate itself back to zero. And the process of doing so is going to be interesting and maybe closer in the future than we think it is. Not any time that we're going to worry about. But I think the lambda, the expansion constant, should be something that levels off at some point and then, in a sense, actually reverses. And the reason behind that is everything goes back to zero. And since I'm a dual universe person, I think there's another universe lurking out there just saying like, all right, come back, time to come back. And when you come back, it goes back. And essentially, they both curve back on themselves. And that produces, I think I put the slides out for this. I did an elaboration of some of Penrose's ideas in which I added a dual universe theme to it. I can't remember if I think, I know it's on my website somewhere. I've got it out there, but you can see some figures in which I show the curvature, the expansion of the universe as actually being a component of a 5-dimensional torus, and that you get this interesting curving thing. And again, it's just a hypothesis, but I mean, I actually think it does a pretty good job of explaining some aspects of why acceleration is expanding, and it eventually will slow down. So, and it's predictive. It actually says that the annihilation of our universe would be not through just expansion. Penrose wanted to just keep expanding things. I don't think that works because protons just don't work that way. But the suggestion I was making is that they would annihilate eventually, that they would come back to this other universe. And then you get this re-expansion from these dual universes. Now, Penrose is not a dual universe person as far as I know, but it does make an interesting twist on the expansion constants on how to do that. Makes for some pretty diagrams too. It suggests that time is actually a force. Yeah, conform. Yes, CCC. If you look, I think the title on my website, Apabistia Notes, is quantizing on quantizing general relativity, something like that. It's near the bottom of the list. I don't have any organization in my list, but if you want to see some pictures on a different interpretation of what the expansion is. The idea of dual universe, and since you brought that up about expansion, I got to mention it. I think we have dual universe physics going on all the time when we talk about virtual particle pairs, because think about it. If you put a positron and electron together, what do you get? You get a big bang, huge bang in terms of the electron. You get gamma ray, 2 gamma rays, sometimes 3. So you get a big bang if you put a gamma ray and a positron. What happens if you put a virtual particle, positron, and electron together? You get nothing. It goes, just evaporates. That's usually explained in terms of space-time uncertainty. An alternate explanation is that you have 2 different forms of electrons and positrons, and that one of those forms could either be the electron or it could be the positron, has negative energy. So when those 2 go back together, what you're really getting is you're getting from nothing, you get a pair, just like a momentum pair, except in energy, then it pops back together. Well, the other proposal is that happens all the time in our universe, but also it's the basis of the broader structure of our universe. There's actually a much larger scale, enormously slower version of that, and for which we should be very happy, because without the invention of time and the relationships that create time, it would happen so fast that we wouldn't be here. So, but I think there's some interesting issues about where the expansion might come from. I haven't looked lately at what he's been doing on CCC. I should look back at that. I just remember that and this was an objection Sabina Hassenfelder had also, that protons, protons in particular, just don't, no matter how big you make the universe, Penrose's idea was that eventually it just becomes nothing again. That it becomes so diffuse that there's no structure to it and can rescale. And I agree with Dr. Hassenfelder on that, that I don't think that's an accurate description of what we see from particle physics. But I still like that. Never underestimate anything Penrose says. I mean, that is an amazing mind, and he's just worth taking seriously and trying to explain, which is why I played around with that idea some and tried to put it in a dual universe version. Other questions?
Ron has a comment. Single photon detection devices do exist and are used in quantum sensors. Is Ron's
Oh,
comment.
yes. There's great stuff going on with single photon emission detection, and those devices just I just love those because they bend your mind about what a photon is and how it works. So all those examples I gave, like if you use that single photon emitter and detector and put it in a giant telescope in reverse, and put your detector somewhere way out beyond Pluto, put a huge detector out there, you could, in principle, engineer a thing where that single photon would be so well defined in terms of its wave packet that it would arrive with near 100% certainty at that distant post. So yeah, they're just exploring those domains of where they kind of break your mind about saying how much structure can a single photon. I've known Sabina long enough. I knew her before she was famous, so I remember sending her a comment once and saying, you could be really good at this YouTube thing because she has that sharp sense of humor, which I love, and just I like the little remarks that she makes with that. She used to have a group called Back Reaction, and it was a fairly small group, and we had a lot of fun discussions, a group of us back then. But YouTube called and essentially they forced her. She didn't even want to go to YouTube. They kind of forced her into it. So because they were giving all the support to that, and I think it worked out well for her. So, but yeah, it's always interesting when you see people that you've known from a different context. Jan LeCun comes to mind, and you see them become genuinely famous people, and it's just. It's kind of fun and it's kind of amusing at the same time because I have a very mellow view about the being famous has good points and it has bad points. So there's always a risk factor in something like that. But watching Jan LeCun, wow, he was one of many researchers, but man, he had some interesting ideas in terms of his early devices. I remember at MIT once he just scanned this new device. He just got a custom chip and he just scanned the lens around the room, and it was identifying objects left, right, and sideways. And nobody could do that at that time. That was completely undoable with the technology at that time. So yeah, he became famous for a good reason with that. Um, and that's a very different use of that technology from what's going on with large language models. So yeah. Any other questions?
So far, I don't see any question on the chat or on YouTube. So if you want to ask question, please unmute and ask online. So I remember Terry will have another talk on October 11th. It's about the $1 million prize.
Yes, I remember the sequence now. And I'm actually serious about that. But the trouble is if you win the prize, it's going to take you 10 years to get it at a minimum. But it's still an interesting prize. And I get back into some of the issues of the mathematics of symmetry groups and how you might kind of dive in from a different direction and see if you can bring something out of that. That was probably the most difficult of the Millennium set of prizes in the sense that it was probably more ill-defined than some of the others, to be honest. But it's still an interesting question. And it was back in a time period where people thought continuum mathematics had the solution to everything in physics. And in case you didn't notice, that I am not of that school. So continuum physics, I would say, can be a bit illusory. So I gave a very different spin to it and a very presumptuous set of goals, but I think there might be some ways to work around it. So it's a serious presentation. I would love to put it out and see if there's people could analyze it a little differently.
I got a
Thank you,
good
Masha.
feedback. Yeah. Thank you, Professor Bollinger, for sharing your knowledge and your thoughts, your honesty, and these fantastic 2.5 hours.
It has been 2.5 hours. Thank you all for the great questions. This has been a fun session.
Any other questions? Yeah, if not, let's call off this meeting and we'll have another one on September 21st, early in the morning at 9:30 a.m. And Terry will have the next talk on October 11th.
Okay. Thank
See
you,
you.
everybody.
Thank you. Thank you for coming. See you.